Hello friends, in today's question, two non-viscous, incompressible and immiscible liquids of density ρ and 1.5 ρ are poured into two limbs of a circular tube of radius r, and a small cross-section kept fixed in the vertical plane as shown in figure. Each liquid occupies 1/4 of the circumference of the tube. So we have to find out two things. Find the angle theta that the radius to the interface makes with the vertical in equilibrium position. And part B, if the whole liquid column is given a small displacement about its equilibrium position, show that the resulting oscillations are simple harmonic. Find the time period of these oscillations. So this is the tube, and we have two liquids, and they are incompressible and they are not able to mix with each other, having a different density ρ and 1.5 ρ. Okay. And we are going to find out, in first case, the angle theta with the interface. So this is the interface where the two you can say two liquids are meeting with each other but not mixing. Okay, this is a boundary sort of. So let us first of all draw this figure in a little more bigger way. And this is the vertical section. This point is given as O, and the liquid is, you can say, this is the upper boundary of this, and let us call this point as A, this point as B, and the intermediate boundary is, let us call this as C, and this C is making an angle of theta with the vertical. And we are supposed to find out what will be this angle of theta in the equilibrium condition. It means these two liquids will be in equilibrium. So this is the first liquid up till here, and this is the second liquid. So yeah, so let us start. It is said that each liquid occupies 1/4 circumference of the tube. It means the angle made by the respective liquids will you can say at the center will be equal to 90 degree. Okay. You can say that since each liquid occupies 1/4 of the circumference, then we can write angle AOC will be equal to 90 degree, and that will be equal to our angle BOC. And let this is a directly, you can say, midpoint of this entire system. Let us call this as point D, and we can say the pressure at this point D in the equilibrium will be equal. It means pressure because of the liquid that is in AD will be equal to the pressure that is because of DB. In the DB there will be two types of liquid. One will be having a density of ρ, and another one will be having a density of 1.5 ρ. So from here we can say that at equilibrium, pressure due to this dB will be equal to pressure due to DC plus pressure due to CB. Pressure due to CB, and let's call this as P2. Okay. And we can say that pressure due to AD at point, or we can say at interface point D. And here also I forgot to mention pressure due to dB at interface point D. At interface point D is taken as P2, and pressure due to AD at interface point D, let us suppose that is taken as P1, and P1, because of this, you can say AD, this part, this is taken as P1, and this entire portion pressure is taken as P2. So P1 will be equal to density of 1.5 rho g, and H1, we suppose that the height of this liquid is our H1. Okay, we will draw the figure later on. And for P2, let us solve first of all this P1. So with this, we have this center as O, and this is point A, and this is point D. So this is the height of the you can say liquid above the point D. So let us call this as H1. And we have this angle is theta. So if we join this one will also theta, and let us call this as point P. So this will be our point P, and angle will be theta. And also for this portion, we are going to have this angle will be also theta, and let us call this as point as Q. And for this portion, let us call this as point as N. Okay. Yeah. So for P1, this is our AD. So we have to suppose to find out what will be this height. So total is our radius R, and this height, that is PO, will be equal to our R sine of theta. This will be R sine of theta. So sorry, I missed. So total height is R, and this is angle theta. So therefore we can say this PO will be equal to R sine of theta. So PD, that is height H1, will be equal to R minus R sine of theta. So we can write that our OP will be equal to R sine of theta. So therefore our H1 will be equal to R minus R sine of theta. Therefore we can write that our P1 is equal to 1.5 rho g, and this becomes R minus R sine of theta. So we got the value of P1. Now we are going to find P2, and P2 is a combination of pressure due to this DC part and then pressure due to this BC part. So therefore let us first of all sort for this DC. So we have this as point O, and this is our point C, and we have this as D, and this is the respective height of the, let us call this as H2. Once again, this is angle theta, total is our radius R, and we took this point as N, so we can say NO will be equal to R cos of theta. This will be our r cos of theta. Cos of theta. So you can say that pressure due to this, and this is our DC. Therefore, pressure due to DC, pressure due to DC will be equal to 1.5 rho G and H2, and H2 can be written as R minus R cos of theta. So therefore we can say that pressure due to this DC will be equal to 1.5 rho G, and this becomes R minus R cos of theta. So we found out this pressure due to DC. Now we are going to find out pressure due to CB. So we can once again draw the diagram, and we have, this is our center O, and this is our point C, and we have, this is our point B, and we just said that this angle is theta, and this is the height of the BC. Let us suppose this is H3. Now H3, this we consider point as N, and this point as we consider Q. So we know this angle is theta. We just found out that our NQ, or we can say NO, sorry, this NO is our R cos of theta, and our OQ will be equal to R sine of theta. Okay. So you can say pressure due to this BC, so this is our BC, pressure due to BC will be equal to, this will be our rho G H3, and H3 is our, we have R cos of theta plus R sine of theta, R cos of theta plus R sine of theta. So therefore pressure due to BC is equal to rho G, and we get R cos of theta plus R sine of theta. Okay. So therefore our P2 will be equal to pressure due to DC plus pressure due to BC, and DC is our 1.5 rho G, R minus R cos of theta, and plus pressure due to BC is our rho G, and we have R cos of theta plus R sine of theta. And at equilibrium, the pressure of P1 about point D and pressure of P2 about point D will be equal to, they will be same. You can say at equilibrium P1 is equal to P2 about interface point, D. So we substitute value of P1 was our 1.5 and rho GR, this will be 1 minus sine of theta, and rho GR we can take common from here, so you can say this is rho GR, and we are left with 1.5 minus 1.5 cos of theta plus cos of theta plus sine of theta. Rho gr cancels out, so we multiply it inside, we get 1.5 minus 1.5 sine of theta is equal to, this is 1.5 minus 1.5 cos of theta plus cos of theta plus sine of theta. This 1.5 and this 1.5 cancel out, so we have here minus 1.5 sine of theta, and here we have sine of theta, so this becomes minus 2.5 sine of theta, and this is minus 1.5 cos theta, and this is plus cos of theta, so this becomes 0.0 cos of theta. Minus and minus goes away, so we can write this as sine of theta oblique cos of theta, and this will be equal to 0.5 divided by 2.5, and that is equal to 1.5. So therefore we can say tangent of theta is equal to 1.5, or theta, sorry, 1 upon 5, and theta is tangent inverse of 1 by 5. So this is the value of theta, okay, angle. So you can say this is the value of theta, that is angle. This is the value of theta. So we just completed our first part. Now we start our second part. In the second part, it is said that if the whole liquid column is given a small displacement from its equilibrium position, show that the resulting oscillations are simple harmonic. Find the time period of these oscillations. Okay, we are supposed to find out if it is given a simple push. Okay, but before that, we just want to find out one more thing, that about this point D. In equilibrium condition, the torque that is being produced by AD will be equal to the torque that is being produced by this torque that is being produced by the density of 1.5 will be equal to torque that is being produced by density of rho, okay, in terms of density. So let us redraw the figure again in terms of the densities. So this is our central axis. This point is given as D, and we are having, this is our center, that is O. So somewhere here there is C point, and somewhere here there is A point, and across this it is here B. So this is A and this is our B. Okay. And for this entire section, this is one liquid and this is the second liquid. So for this entire section, we assume that somewhere here the center of mass for this entire liquid lies. Okay. So let us suppose that is given as M1G, and for this entire section of this BC, the center of mass lies somewhere here, and that is given a M2G. So we can say that at equilibrium, the torque about point O will be equal. So which means that torque due to density of 1.5 rho will be equal to torque due to density of the rho, and 1.5 is going to give us, okay, and let us draw the perpendicular distance. So this mg, let me draw this figure again here independently in order to show this. So this is point O, and this is our vertical line, and this point is given as P. Sorry, P we have already taken. Let us suppose this point is our R. So this is our R, and we have m1g in the downward direction, and the other point, let us take this R prime, and this is our R prime, and we have here m2g. So this, let us call this point as N, and we have already taken. So let us call this as O prime, and this point as O double prime. Okay. And the angle between this angle will be 45 plus theta, and this angle will be 45 minus theta. Okay. The angle between the center of mass. This line and this is our center of mass. So this is our R, and this is our R prime. And if we join this to a vertical line, so we said this is our O prime, and this we call this as O double prime. Okay. And we know this angle is our theta, so we are going to get entire angle is of 90 degree. So center of mass, this will be giving us 45 minus theta, and other part will be giving us 45 plus theta. So therefore we can write the equation of the torque. We get this as our m2g, and we can write this as m2g and multiply by O prime R prime, and we have m1g multiply by O prime R. So we substitute the values. We get this as m2g multiplied by our O prime R prime will be equal to R, this is R, and we get this as R sine of 45 plus theta. This becomes R sine of 45 plus theta is equal to m1g, and this becomes our R sine of 45 minus theta. Okay. This was our in equilibrium condition. Now in the question it is said that it is given a small displacement. Okay. So if we assume that it is given a small displacement in this direction, then this point A will be somewhere here, and this point B will be somewhere here. So let us suppose this is point A prime, and now this is B prime. Now this we assume, let us suppose it is given a small push by angle of alpha, and this angle will be also alpha. So we say that the liquid is displaced, the liquid is displaced by a small angle alpha. Okay. Now if it is you can say displaced by a small angle alpha, then this angle becomes 45 plus theta plus alpha, and this angle becomes 45 minus theta minus alpha. Okay, there will be a marginal in the m2g, there will be addition of alpha, whereas for m1g there will be a subtraction of alpha. Okay, so therefore now as the liquid has been displaced from the equilibrium position, there will be net torque between the two liquids. So therefore we say, therefore the net torque, let us call this a tau net, and we can write our tau net will be equal to m2g, and we have this is r sine of 45 plus theta plus alpha, and this becomes our m1g r, and we have sine of 45 minus theta and minus alpha, and we can substitute the value m2. We can write this as rho v gr, and we have here sine of 45 plus theta. Let us combine this term and plus alpha. We are going to open this using the trigonometric identity, and this becomes 1.5 rho v gr, and here we have sine of 45 minus theta and minus of alpha. So we can take common rho VGR from both the equations. So we are left with rho VGR, and this we can just open using the trigonometric identity. We can write this as sine of 45 plus theta, and we have here cos of alpha plus cos of 45 plus theta, and we have sine of alpha. For the second term minus, and we have here 1.5, so this becomes sine of 45 minus theta and cos of alpha minus cos of 45 minus theta, and this is minus of sine of alpha. Okay, now from the equilibrium position, that is, let us call this as equation number 1, we are going to consider this equation, and we say from equation 1 we can write that our m2gr sine of 45 plus theta is equal to m1gr sine of 45 minus of theta. So we already know m2 is our rho vgr sine of 45 plus theta, and this becomes 1.5 rho vgr sine of 45 minus of theta. So here rho vgr cancels out, so we get that sine of 45 plus theta is equal to 1.5 sine of 45 minus of theta. We are going to use this relationship and substitute in this equation. Okay, let us call this equation number 2. So we can say, using equation 2, let us call this equation 3. Using equation 3 in equation 2, we get rho vgr is common. We have rho vgr was common, and inside we can write this as 1.5 sine of 45 minus of theta, and we have here cos of alpha plus cos of 45 plus theta, and we have here sine of alpha, and this comes as minus 1.5 sine of 45 minus theta cos of alpha, and this becomes plus 1.5 cos of 45 minus theta and sine of alpha. So these two terms cancels out, so we are left with now rho vgr, and this is our cos of 45 plus theta, cos of 45 plus theta cos of alpha plus 1.5 cos of 45 minus theta, and we have sine of alpha. So here it is sine of alpha, not cos of alpha. Sine of alpha. Sine of alpha we can take common. We are left with rho v gr sine of alpha, and we have here cos of 45 plus theta plus 1.5 cos of 45 minus of theta. But it is said that this angle alpha is small, so we can say sine of alpha will approximately equal to alpha. For small angle alpha, sine of alpha is approximately equal to alpha. So we can rewrite this equation as rho v gr, and this gives us cos of 45 plus theta 1.5 cos of 45 minus theta, and here comes our alpha. So from this equation, and this was our torque net. So from this equation we can clearly see that this we take as k, then we can say our tau net is equal to k, where k is value of this entire equation is equal to alpha multiplied by alpha, or we can simply say that tau net is directly proportional to our alpha. So therefore we can say that this shows that liquid column executes SHM. Okay. And for k we can consider this value, that is rho v gr, and we have cos of 45 plus theta 1.5 cos of 45 minus of theta. So this is the value of k, which we are going to use later on also. And now it's a simple calculation. Now because of this torque, there will be also a moment of inertia that will be introduced. So let us calculate the moment of inertia. We say moment of inertia about point O. So we have two liquids, and both liquids are going to generate different moment of inertia. So we can say total moment of inertia I is equal to moment of inertia because of the liquid having density rho, and second will be moment of inertia having liquid density 1.5 rho. So therefore, as the mass is m1 and m2 and the distance from point O is same, that is r, so we get total moment of inertia I will be equal to m1 r square plus m2 r square, and we can write that m1 will be equal to rho multiplied by v r square, and this becomes 1.5 rho v r square. Therefore total moment of inertia will be equal to 2.5 rho v and r square. So we know that the equation for the time period for the SHM, which is having a moment of inertia of I and constant is k, we can write that the time period of oscillation t will be equal to 2 pi square root of moment of inertia I divided by k. So we already know I and k, we substitute both values, so we get this as 2 pi, and we have here square root of I is about 2.5 rho v r square, and k we know is rho v gr, and we have here cos of 45 plus theta plus 1.5 cos of 45 minus theta. This rho v and r square cancel with this r, so we are left with only that 2 pi square root of 2.5 r divided by g, and here we have cos of 45 plus theta plus 1.5 cos of 45 minus theta. So let's calculate this value. We can write this as cos of 45 plus theta, and theta we know, we just calculated the tangent of theta is equal to 1.5, so theta will be equal to approximately 0.197 radians. Okay, so we write this cos of 45, we can write in radian 0.78, and this becomes 0.197. So we get this as cos of 0.98, which is approximately equal to 0.55, and we find out next term, that is cos of 45 minus of theta, so this becomes cos of 0.78 minus 0.197, and this will be equal to cos of 0.58 and approximately equal to 0.83. So we substitute all these values, and we can say our time period t will be equal to 2 pi square root of 2.5 r and g, and this is further multiplied by 1.5. Okay. So we can write this will be equal to 0.55 plus 0.83 multiplied by 1.5, and this gives us approximately the time period will be equal to 2.83 square root of r. This makes seconds. So this was quite a lengthy question, but the only thing which we keep in mind that with respect to torque with the equilibrium and when it is, you can say, pushed by small angle of alpha, and we are going to equate them, solve it, and get the time period of the oscillation. So you can say this is the time period of oscillations. This completes the question. Thank you.